Picture this. You're sitting in your Cambridge IGCSE physics exam, staring down a heavy collision question. You think you've got it completely figured out, but relying on one simple, popular shortcut is about to literally cost you a full letter grade. We are upgrading your final minute revision plan into a top band scoring system. Right now, let's go. So why does the seemingly innocent P equals MV shortcut instantly cost you 3 marks? Well, it happens because treating momentum as just plugging numbers into a formula without actually considering vectors is a fatal trap. It's a mistake examiners see all the time.
Okay, let's dive into this. To survive the exam, we have to define the key word exactly as Cambridge wants it. A vector is a variable that has a magnitude, meaning its size, and a direction. And let me tell you that single word, direction, is exactly what separates a generic failing answer from a top band score. Momentum is a vector quantity, so its direction is always going to be that of the velocity. This brilliantly illustrates how we apply that definition in a real calculation. We really only need to consider motion in a straight line here. Velocity and momentum values in one direction are positive, right? And in the opposite direction, they've got to be negative. It is an absolutely undeniable rule. If you miss that negative sign, everything that follows is completely wrong. No marks.
To guarantee you never make that mistake, you need a system. This right here is the core framework that turns ordinary revision into an unstoppable top band scoring machine. Step 1, start with the concept. Step 2, grab the evidence or data. Step 3, apply scientific reasoning. And Step 4, use exact examiner wording. Let's see how this builds when we apply it to a real scenario. Look directly at the diagram, straight from the source text, showing the conservation of momentum for 2 objects. Focus specifically on the bottom collision diagram. After the collision, Object 1 and Object 2 are both moving. And because they're moving along that straight line, their directional velocities are going to dictate the entire mathematical outcome. Which brings us to our main concept. Momentum before an event equals momentum after the event. This is the conservation of momentum. It's the golden rule, the absolute foundational concept for any collision question Cambridge can possibly throw at you. So, the absolutely crucial point here is how we write that out mathematically. Think about this carefully as we pace through it. Mass 1 times initial velocity 1 plus mass 2 times initial velocity 2 equals mass 1 times final velocity 1 plus mass 2 times final velocity 2. You really need to notice the specific difference here. The U represents velocity before the collision, and the V represents velocity after. Don't mix those up. In a moment, I'll show you the exact examiner clue regarding the impulse equation trap that completely changes your final answer. It's a trap that catches out 80% of students. But first, you need to understand the mistakes that make that trap so dangerous. Can you spot the errors students usually make? Let's look at these and build our awareness of what absolutely not to do. These are the painful, mark-destroying mistakes Cambridge examiners see constantly. Missing your units, rounding way too early, giving vague explanations, and using the wrong variables. Now, what's really interesting here is the direct comparison. On the left, we've got a flawed student answer. They calculated the final momentum perfectly, but totally ignored the negative velocity of the opposing object. Basically, they treated a vector like a scalar. Ouch. On the right, we have the top band examiner-approved answer. Notice how they assigned a negative value to the opposing object's velocity? They perfectly preserved its vector nature. That single negative sign is literally the difference between passing and failing this question. All right, let's escalate the stakes a bit. Because our framework doesn't just protect you in momentum questions, it saves you in equilibrium curveballs too. Take a look at this moments in equilibrium scenario. We have a crane lifting heavy steel girders. It has a jib arm that is 30 meters long in total, and the problem tells us to assume the jib itself has no mass. Let's zoom right in on the data. See that massive concrete balancing weight? It's 10,000 newtons, positioned exactly 5 meters to the left of the pivot. That is our known anti-clockwise moment. Just force times distance, 10,000 times 5. Simple enough, right? So here is your interactive challenge based on the framework we just discussed. What is the maximum weight of girders the crane can lift on the right side at a distance of 25 meters from the pivot? You have to balance the clockwise and anti-clockwise moments. Think about it for a second. Got it? The left side gives us 50,000 newton meters, so the right side must also equal 50,000. Divide that 50,000 by the 25-meter distance, and you get exactly 2,000 newtons. That is your maximum weight. Fantastic work! Now, as promised, let's pivot back and resolve that open loop to confront the final, most dangerous concept on the source page, the impulse trap. Here it is, the impulse equation. Force times time equals mass times final velocity minus mass times initial velocity. Or, simply, Ft equals mv minus mu. The fatal mistake here? Students constantly confuse u, the initial velocity, with v, the final velocity, when calculating the change. It sounds basic, but under exam pressure, it happens. If you swap them, your mathematical sign reverses, and boom, you lose the marks. And remember, Cambridge actually allows two distinct ways to define impulse, straight from the source text. You can define it as the force on the object multiplied by the period of time over which it acts, or you can define it as the change in momentum of the object. Knowing both ensures you can adapt to however the examiner decides to word the question. Okay, we are entering the final sequence. Before you ever hand in that exam paper, you absolutely must run through the final examiner's safety checks. This is exactly how you secure every single available method and final mark. Do not skip this. Rapid fire. Here are your definitive checks. Ensure all substituted values have the correct units. Verify your final answer includes the correct units. Confirm you avoided rounding too early in your intermediate steps. And finally, check for reasonableness. Seriously, if your crane is lifting 3 billion newtons, you've definitely made a math error somewhere. You now have the ultimate framework for momentum, vectors, and moments. But listen to me, mastering these equations is completely useless if you fall for the traps waiting for you in the next major subject area. Everything you just learned must be protected by mastering the next set of common question traps. I've actually mapped out the safe shortcuts for the entire syllabus in our next explainer. You absolutely need to see that full revision map to survive this exam paper. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click over right now, and as you do, ask yourself, are you just memorizing equations, or are you finally mastering the physics? I'll see you there.